All right, in this example, we're going to look for continuity of a piecewise function. So this is something we've actually already talked about, but just an additional example to kind of help you make sure you're clear about everything that's going on. So you could consider continuity of this function without a graph, but my advice would be that if you can draw the graph, if it's not too hard to draw the graph, I would suggest drawing it because it's a big help in thinking about continuity. So you need an accurate graph. That means if you can't draw it by yourself, you can use technology, but you need to be aware of any place where technology is a little bit glitchy. Fortunately for this problem, the pieces of the piecewise function are all very simple functions that we're pretty clear about what the graph looks like, so we can get a good graph by hand or using technology and being aware of what the technology is showing us. So just notice here that on the piecewise function, I've got constant functions for two of the pieces, and then a line, y equals 4x for one of the pieces, and a very simple parabola, y equals x squared for the other piece. So because these are all very simple pieces, this is a pretty straightforward one that you can draw the graph by hand. If you need to use technology to help you with any of those pieces, that's okay. You want to be aware of what's happening at the end points, which is where the technology sometimes has a little bit of difficulty with these kinds of functions. All right, so the first thing I'm going to do is draw a graph of the function over here, so xy coordinate system. I'm going to do a little bit of scratch work down here too, and you don't have to do this scratch work, but if you're having a hard time still graphing piecewise functions, sometimes the scratch work can help. So for my scratch work, what I'm going to think about is the graph of each of these functions separately without worrying about these restrictions for x. So I'm going to think a little bit about the graph of y equals 4, f of x equals 4, or y equals 4. That is a horizontal line at y equals 4 with slope 0. So any constant function is just a flat line at that y value. So f of x equals a constant or y equals a constant. So I don't want that whole line, though, on my actual graph of the function we're trying to graph. I want only the part of that line where x is less than or equal to -2. But for my scratch work, I went ahead and just drew the whole line so I can think about that shape. And now I'm going to think about, well, where is the part of that line where x is less than or equal to -2? So I'm going to think on my graph here. Let me put a scale on the x-axis. So here would be -2, and there's 4. And so the point where x is equal to -2 would be right there at -2, 4. And then I want the part where x is less than -2. So that would be the negative side of 2. So toward the further negative numbers. All right, so that is the part that I'm going to put on my graph of the actual function. I graphed the whole thing to help me think about the shape. And that's what you're going to graph on your calculator, that whole function. And then you just want to think about the part of it that you actually need to sketch here for the piecewise function. All right, so up here on my actual graph, I'm going to put at the point -2, 4. Notice that x is equal to -2, so that is an included point in this graph. At that point at -2, 4, I'm going to go ahead and label those coordinates. You don't necessarily have to do that, but that's going to help us. And then I want the part of that where x is going further to the left, so negative direction. Okay, I'm going to do the same thing with these other pieces, so I'll go maybe a little bit faster through some of those. Another piece of scratch work down here, I'm going to think about the graph of y equals x squared. And I'm going to think about the whole graph of y equals x squared, and then I will worry about the restriction that's here. So y equals x squared, that's a basic parabola, vertex at the origin, opens upward. You can plot a few points if you want to. Those are very easy to think about, especially when x is positive. Put in 0, x equals 0, you get y equals 0. Put in x equals 1, you square that, you get y equals 1. X equals 2, square that, you get y equals 4. And because of the symmetry with respect to the x-axis, once you get one side, you can figure out what the other side looks like. So maybe you know those without having to think about those points, but you can go ahead and do that. So that's the whole graph of y equals x squared. But what I want to graph up here is just the part of that graph where x is between -2 and 0. So this inequality says -2 is less than x is less than 0, or x is between -2 and 0. Notice on this inequality, I don't want where x is actually equal to 0 or where x is actually equal to -2. So I need to be sure I know how to indicate that on this graph. All right, so at x equals 0, that would be the point at the origin, but I'm going to use an open circle when I graph that on my other graph here at x equals 0, because that point's not included. At x equals -2, that would be up here at -2, 4. I thought about that as I was kind of plotting these points, and I want the part where x is between 0 and -2. All right, so because I drew over the graph that was already there, maybe it's a little hard to see those open circles, but when I put that up here, we should see those open circles at -2, 4 and at 0, 0. All right, so at 0, 0, I have an open circle. And then I would like to put an open circle here at -2, 4. That happens to be where there's already a point from the other piece of the piecewise function. So in some way you can think about that the point that's there is filling in the hole or the open circle that I would be wanting to draw there. So when you draw that, it's just going to look like a point right there where this piece connects to the other piece. Okay, so there's that part of the parabola, and again, the point that was on the graph of y equals 4 happened to fill in the hole on the parabola at -2, 4. So those connect. So that's a filled in dot right there. Okay, next piece, y equals 4x. I'll just go ahead and do that down here. Y equals 4x. So that is a line, a y equals mx plus b form. The m is 4 and the b is 0. So that is a line through the origin with slope 4. So if I draw the whole line, I just put the b was b0, the y-intercept is 0, and slope is 4. So I counted up 4 over 1 for rise over run. So that's the whole line, y equals 4x. I only want the part of that line where x is between 0 and 1. And not including those endpoints. Again, notice there's no equal to right there. So I drew the whole line on my scratch work. Again, if you're better at these, maybe you can just think about the whole line and know what to sketch here. But if you're struggling, my advice is to draw out the whole graph and then just take the part of that graph you want and put it on your actual graph. So at 0, we're here at 0, 0. Again, an open circle because it doesn't have equal to. And then 1, 4 is going to be where this other point is, and I want the part of that graph where x is between 0 and 1, so right there. Okay, so I'm going to put that up here. All right, so I have an open circle at 0, 0. There's already an open circle at 0, 0. If there weren't, I would draw one there. It's not going to fill in. I don't have a point on either of these graphs at 0, 0, so it's not going to fill in. And then I'm going to go over here to 1, 4, and that's where I'm going to have another open circle, and that's a straight line connecting those. I'm going to go ahead and label 0, 0, and I'm going to put there open just to remind myself that that is open. We'll see what happens with this other piece, whether that open circle gets filled in or not, but so I'll label that in a little bit, but just to be clear that this is an open circle here. All right, this last one is y equals 1. So similar to y equals 4, that is a constant function. That would be at y equals 1. So right there at y equals 1, and it's just going to be a horizontal line at y equals 1, slope 0. And then the inequalities here are a little bit different. So I just want to point out kind of what it's saying about that. So I have that line, but I have really two different things here. So I have that line at x equals 0, specifically at x equals 0. This is not an inequality. This is just saying at x equals 0. So that would be on that line at the point x equals 0. So we have a point, just a single point right there at x equals 0, filled in because x is actually equal to 0. So that's the point 0, 1. And then the other part of that line I want is the part where x is greater than or equal to 1. So this is not saying anything about what's happening between 0 and 1. That's actually described up here, right? Just at x equals 0, and then for x equals 1 and x bigger than 1 over here. So here's x equals 1. I'm going to put a filled in dot there because x is equal to 1 on that part. And then x greater than 1 would be to the right of that. Okay, so now I want to put that up here on my other graph. So I have a single point, an isolated point right here at 0, 1, and then I have this line segment over here starting at x equals 1 and going to the right. Okay, so single point right there at 1, 1. I'm going to go ahead and label those coordinates. That is an actual point. And then, sorry, that's 0, 1. 1, 1 is over here, an actual point, and going to the right. So 1, 1. And then I said I would label this as soon as we figured out what was going on with the last piece. This up here is going to stay open. There's nothing to fill that in. So that is a point at 1, 4, but that's open. So there's not actually a point there. It goes right up to that point, but not including that point. Okay, so I spent a lot of time talking about graphing this piecewise function, which maybe you already knew how to do, but most students at this level still have a little bit of trouble with graphing piecewise functions, so that's why I wanted to take a while to talk about that. But really what we're after here is talking about continuity of this piecewise function. So at its sort of conceptual level, continuity is about whether or not the graph has breaks in it. So if I look at this graph, I see that there are some breaks in the graph. For example, this line y equals 4x and this line y equals 1 do not connect. There's a break between those two. There are some other places where there are breaks in this graph as well. So continuity is about whether or not there are breaks. So kind of the formal language for that, we want to think about where this graph has discontinuities. And that's actually where I would start, even if the question asks about continuity. I would look for discontinuities first. Or we might also call these places where the function is discontinuous. So discontinuities or places where the function is discontinuous. So what I'm looking for on this graph are any places where there are breaks in the graph. So provided the domain of the function isn't restricted, so that happens when you have things like fractions where the denominator might be 0, radicals where the expression inside them might be negative, and then that causes some domain restriction, some other things related to that. Provided you don't have any of those kinds of things. Notice for these functions, I don't have any denominators to worry about. I don't have any radicals to worry about. Provided I don't have any of those kinds of things, really, when I think about discontinuities, I'm thinking about breaks in the graph. And for a piecewise function, those could happen where the pieces join up. So the potential places where I could have discontinuities on this function are at x equals -2, at x equals 0, and at x equals 1. I don't actually have discontinuities at all those values, but those are the places to consider whether I have discontinuities at those places. All right, so I want to look at x equals -2. That's where these two functions switch. And what I'm looking for is there a break in the graph? There is not a break in the graph. That function is continuous at x equals -2. At x equals 0, I do visually see a break in the graph. I have two pieces of a graph that are both going toward the same place, but I have this other point that is disconnected from the rest of the graph at that point. So at that point, I do have a discontinuity. We'll write a little bit more about that down here. And then looking at the graph, also at x equals 1, I have a place where the graph breaks. So that's another place where I have a discontinuity. All right, so I have discontinuities at x equals 0 and x equals 1. Sometimes that's all you really need to say is where are discontinuities. But sometimes you will be asked to say what part of that definition of continuity fails. So this is where you need to go back and think about definition of continuity. So I have a discontinuity at x equals 0, and there are three conditions in that definition that you need to check. The first one is, does f of 0 exist? So that's asking, is there a point at x equals 0? There is. There's a point at x equals 0. It's at y equals 1. There's a point there. That's the first condition in that definition of continuity. The second condition in the definition of continuity is, does the limit exist as x approaches 0? So that's about being close to x equals 0 on both sides on the graph of the function and looking at when you get closer and closer and closer to x equals 0, is the function headed to the same place? It is. It's headed toward this open circle there. It doesn't actually touch that open circle there, but that's the limit as x is approaching 0. So that second condition is met. The limit does exist as x approaches 0. And then the third condition is, do they agree? does the point agree with the limit? And that's the condition that fails here. I have a point, f of 0 is 1. I have a limit, the limit as x approaches 0 of f of x is 0, headed toward that place, but these do not agree. So that's that third condition. In the definition of continuity, it's the third condition that fails here. So if any of the three conditions fail, the function is discontinuous at that point. Visually, you can see the discontinuity pretty easily. The theory about justifying why is what's happening here. Okay, and then the other place I can see a break in the graph, see a discontinuity, is at x equals 1. So let's think through those three conditions for that one. So at x equals 1, do I have a point? I do. There's an open circle here. That's not an actual point. That's the graph going right up to that point, but not an actual point there. But I do have a point here at x equals 1, y equals 1. So I do have a point. F of 1 exists. It is 1. Then the second condition is about the limit. Does the limit exist as x approaches 1? So you want to think about being on the graph of the function on both sides of x equals 1, and you're going to go toward x equals 1, and those things need to be going toward the same place, and they are not. One of them is headed toward y equals 4, and the other one is headed toward y equals 1. And so the condition that is not met here is that the limit as x approaches 1 of f of x d in E does not exist, since, if you want to give more reasons, the limit as x approaches 1 on the side of 1 that's a little bit less than 1, from the left, is 4. When I'm a little bit left of x equals 1, I'm headed toward 4, and that does not agree, does not match the limit as x approaches 1 from the right of f of x. And I'm on the right side of x equals 1, and I go toward x equals 1, the y value is headed toward 1. So these two have to be the same on both sides for this overall limit to exist. And so that's the condition that fails at x equals 1. Often the question might ask you about discontinuities, but then it probably will also ask you to state the intervals on which the function is continuous. I'll just do that in another color here. So the function f of x is continuous on, so we say that about functions a lot. It is continuous on, it is increasing on, it is decreasing on, it is positive on. So when we talk about a function being something on, we're talking about the x values where this thing is true. So in this case, continuity. So we would say f of x is continuous on all values of x that are in the domain of the function except these. And so looking at this graph of the function, noticing that x coordinates go all the way left and all the way right, the domain of this function is actually all real numbers. So this function is continuous on all real numbers except these two. If I want to write that in terms of intervals, I tend to think in terms of a number line. So I'm visualizing a number line starting at the left side. So I would start with negative infinity, and I would go to the first place where I have an issue. That would be at x equals 0. And then not at 0, so I don't want to include 0 in my interval here. And then it is continuous between 0 and 1 at all these points in here. That's continuous. So 0 to 1, and then right of x equals 1. So from 1 to infinity. So this is how you would write the intervals where the function is continuous using interval notation. This is that union symbol. In online homework, sometimes you need to type that symbol in order for it to count it correct. I don't care if you just put a comma between them or whatever, but these intervals are where the function is continuous. So usually that is what you're going to be asked. You might also be asked this additional thing about discontinuities. But again, my biggest piece of advice is get an accurate graph, whether you can do that by hand or you use technology to help you. Technology is probably going to be great at helping you with this. And then you can take those points and put them on your actual graph with open circles or closed circles at the endpoints. All right, try some homework problems.